Hi everyone. In this lecture, I'll continue with our discussion on the pulse coded modulation. So in the last lecture, we discussed that the problem with the analog communication systems was that the presence of noise was continuously degrading your signal to noise ratio, and when we started adding more and more repeaters, again we discussed what is the purpose of the repeaters and all that, your signal to noise ratio eventually vanishes to zero if your number of repeaters starts to increase. And this was a problem, and the only way to solve this problem at that time was just to increase the signal power indefinitely, and that looked like a very impractical solution after a certain point of time. So then the other solution was to actually convert the analog data into a set of finite values. Okay, now how do we do that? So that's the part of today's discussion, this lecture's discussion. Now what we need to do is that the idea was that, let me tell that again. So the idea was that you convert your continuous signal, which has infinite possible values, to just a finite set of values. You just have to convert it to a finite set of values. Now you already know what those finite set of values are. At the receiver, at the repeater, for example, I said repeater is like an amplifier for analog circuits. At the repeater, now what you need to do is that because you already know which level, the number of possible levels, you just have to make a decision properly which level was transmitted. Okay, if you make the decision properly, if you can make this decision properly, then there is absolutely no error. The repeater can regenerate that known level and retransmit it. Okay, because it knows what that level is, it can generate that level on its own and transmit it again. So that's literally like whatever noise was added before was literally killed. There was no new noise added at all. So that was the advantage of going for digital communications. In that process, if you can see, you can add as many repeaters as you want, because every repeater is going to regenerate the symbols, regenerate the message again and again, because it knows what are the finite levels, so therefore it can regenerate it properly. Okay, then you can actually in theory have input SNR equal to the receiver SNR. There is no alpha and beta factors that we were multiplying earlier in analog communications. So that was the main reason to go for digital communications. Okay, so how do we convert it? So the process of conversion involves two steps. One is called sampling. Okay, the process of converting an analog signal to a digital signal involves two steps. One is called sampling, the other thing is called quantization. Now how do you sample? That was, again, I think I've already made a video on it. So you just have to find, that's when I told you that the Fourier transform, the applications of Fourier transform was taken into account. And then we saw that we Fourier transform the signal, and we said that if you sample it with a certain interval greater than 1 by 2 f max, the maximum frequency in the signal, then you're fine. You can complete there is no loss of information in the signal. They said that, okay, signal, even though it is continuously existing for all time, it really there isn't much information for most of the time. If you can ensure that you take only samples at these time intervals, that is sufficient. You know everything you need to know about that signal. And we said that you can recover the signal back if you ensure this condition with just a finite set of values of the signal. The second step is called quantization. So that quantization is just converting that sample. Now even if I sample it, let's say I just sample the values and I'm plotting this sine wave which is sampled. The second step is called quantization. Even if I sample it, the signal is called discrete time signal, but still the number of values that the signal can take, it's still infinity, because the number of values, it's still a continuous value. The amplitudes are continuous real numbers. They can go anywhere from within the 0 to whatever the maximum value the signal can take. If 0 to V peak is the maximum value the sinusoid can take, this can also take any value in between. The next step is we will round off this to a finite set of values. Between 0 to Vp, I am going to divide 0 to Vp and minus Vp to 0 to a finite set of levels, and I will round off this sample to the nearest possible level. So that process is called quantization. Now quantization is an irreversible process, and we said irreversible process, and we said that we are going to live with some kind of signal to distortion ratio, and this is like a well explored field. It's almost now really nearly, I would say, 100 years, or nearly 100, little less than 100 years of research had gone into this, the theory of sampling and quantization. So we have a reasonably good understanding of this problem now. So this distortion can be very well minimized, okay, by choosing sufficient number of bits and all that. So there is a proper theory for it, theory of quantization, sampling, and how to convert most efficiently samples into set of finite values or bits. Okay, so now the problem is we have converted this signal first to samples, and samples we are reducing it to a finite values, or I'm going to use the word bits. Okay. So if let's say I have an n bit representation for a sample, it means there are 2 power n possible levels, or if I include 0, then 0 to 2 power n minus 1 possible levels for each sample. Okay. So okay, or I can simply say that for an n bit sample, a sample represented by n bits, there are 2 power n possible values, sample values. Now this is called the Ts is called the sampling interval, and 1 by Ts is called the sample rate. Okay. In communications, we are going to call it as symbol. So this sample, in each sample, there are 2 power n possible values that this sample can take, and I am going to call that as a symbol. Okay. Within Ts 0 to Ts, now we are going to transmit a symbol. Okay. Now since it's the value of this symbol is going to be same within this, there is no change. I mean, within this interval 0 to Ts, the value, I am going to now keep that value constant. So you have sampled it, I am going to keep the value constant. Okay. Now the symbol, it's actually one of 2 power n possible values. If I say that I am going to round off to n bits, then it has 2 power n possibilities. So the symbol can be one of 2 power n possibilities. Now 1 by Ts is called as sample rate or symbol rate. Now for example, if this signal, message signal, so I'll take some popular examples of sampling, which we'll again discuss here. So first, when they introduced the telephone, mainly as I said, the whole of digital communications was developed for telephones, they saw that the speed signal had samples going all the way from 300 to 3400 hertz. Okay, this was the maximum frequency. So what they did was that they assumed, okay, the sampling frequency, they chose the sampling frequency. This has to be, of course, twice greater than 2 into 3400. Okay, that comes to around 6800 hertz, 6.8 kilohertz. So they chose somewhere around 8000 hertz, which is 8 kilohertz, which is obviously greater than 6800, 6800 hertz or 6.8 kilohertz. So the sampling rate they chose was 8 kilohertz. And in a pulse code modulation, which is what we discussed right now, you first sample it, and each sample you're now, I'm going to, or you can simply say this is we have a source that has been digitized, it has been sampled at a rate of 8000 hertz or 8 kilohertz. So you have 8000 samples. If this source is sampled continuously and you're looking at the samples of this source, then you can say you are receiving 8000 kilosamples per second. Sorry, 8000 samples per second or 8 kilosamples per second, KSPS. Okay, or I can also say symbols per second. If I am not doing any encoding, I can simply say it's 8 kilo symbols per second. Now each symbol can be represented using an n-bit representation. So we said that each symbol can be quantized. Now if I say n-bit representation, there are 2 power n quantized levels, 2 power l possible discrete values that sample can take. So then I can multiply, then I can have to write 8n kilobits per second. That's the rate at which the sample is arriving. It's being sampled at this rate. So you have the symbol rate, the bit rate is going to be 8n kbps. So there is other word called baud, B-A-U-D, baud rate. It's same as the symbol rate in a communication system. Okay, here I'll discuss, there is a slight difference. What I've discussed right now is sampling directly, and I sampled it and then I spoke about symbol sampling rate. So the more accurate definition for this will be sampling rate. Okay, I'll come to what is symbol rate slightly probably in the next lecture. So here I want to say that if I have a source, I can sample it. Then the 8 KSPS in this case is an example where I've sampled the source with maximum frequency of 3400 hertz. Then I can say 8 KSPS is its sample rate. Now this 8n kbps, 8n, where if each sample is now represented using an n-bit representation, then it becomes, we can say 8n kilobits per second. That's your data rate or bit rate. I can say that as the bit rate. Okay. Now one of the popular cases it was called as a linear pulse code modulation, where each sample was represented using 8 bits. So 64 kbps was the standard data rate. So in this case, I'm using the word data rate. Right now it's just sample rate, so which is directly equal to the data rate in the example I'm taking, but I'll discuss later why am I making that there is a difference between the two. Okay, there is sampling rate and data rate are two different things. So but in this example I'm assuming they are same. So just for your initial understanding, I'll just say both are same. So I can say 64 kbps is symbol rate or sample rate. Okay. Ideally, in this case, it is sample rate, but it turns out it's also a single symbol rate for this. I'll say what is the difference probably in the next lecture. Okay. So you have a 64 kbps of sample rate for this. I can also express it as 8 kSPS, kilosamples per second, or 64 kilobits per second. That's your sample rate for the signal. Now, sometimes your audio signals which are stored and saved in DVDs, the sampling rate in a DVD is 48 kilohertz, and for CDs it was 44.1 kilohertz. These are popular formats of storing. Even today, the digital signals that you hear in very high def musics and all using any computer or any processing devices will have similar sampling rates for audio signals. Okay. So these are, this is something that you should be aware of. For example, 8000 hertz for linear PCM that was used for audio signals. For telephone speaks, for telephony, that is the sampling rate which was used, and 64 kbps was your bit rate of the old telephone systems. Now there is other thing. This is a topic which we will not be discussing in this code. It's called compression or source coding. So first you take your source, digitize it, convert it into a set of bits, ones and zeros. Now each sample, we said, is represented by an n-bit representation. Now by studying the statistics of the source, if for example one sample is occurring most of the time, then you don't need to represent it using equal number of bits. You can represent the source which is most frequently occurring by fewer number of bits, the source which is sample which is occurring very infrequently by a large number of bits. Then the effective number of bits that the source is going to output will be less. So that's just to save either transmission rate or storage rate. Both of them can be saved. If you can represent a source with fewer number of bits, then you are going to save storage space. Okay. And similarly, the transmit rate, you can convey more information in a given symbol. You can say that in a given time interval. You can say that way as well. So in the past, what they did was that they used to sample it with 12 to 13 bit representation, and then they were mapped to 8 bits. So you get a 4-bit compression. You can reduce it by 4 bits, 4 to 5 bits here. Okay, the effective number of bits that the source is going to output will look like an 8-bit 8-bit source, but actually it is a 13-bit representation. Okay, then at the receiver, where you are receiving it, you have to decompress it. You have to source decode it, source encoding and source decoding. So there are 2 operations. That's called source coding together. Okay, and this helped in saving the number of bits you transmit. Sometimes even 8 bits was not sufficient, where the quality of speech was not very high, quality was not required. 4 bits itself was sufficient. The 12 to 13 bit representation signals can be just represented using 4 bits. Okay, and this is again just for your information. So when we discuss the cellular standards, I'll talk about this directly. I will be talking about data rates. So I wanted you to have an idea about what a data rate and symbol rates are. In modern cellular communication, the data rates up to 10 kbps. In fact, if you see, it's much less than 64 kbps. 64 kbps, I said, was the speech, linear PCM that which they were using. So again, what is linear PCM is that here we assume that all the symbols are equally likely. So every symbol is given certain number 8 bits of representation. Later they studied that some sources, for example, used to have the smaller values of the signal. Let's say 0 to V peak is the maximum value of the signal. Most of the time the signal was spending in the smaller values. Very occasionally you used to get large values out of the signal. Then in that case they did something called companding. So they would compress and expand. So they would compress the signal which for large values of VP they will compress it here, and they will expand this region. Okay, so that's called nonlinear operations. That's called companding, compression and expanding. They'll expand the small region and compress the larger values. So that these things you can do provided you know the statistics of the signal a priori. Okay, so again we will not be going deep into this part. This is usually dealt with in a course on proper digital communication, advanced digital communication systems. There is a proper way in which you can represent sources and proper applying probability theory and all that. So here I just wanted you to know these numbers. So where we came, we were initially at 10 kbps speeds. Data rates of initial cellular communications were just 10 kbps with which you could transmit speed signals. Okay, so that was sufficient for audible quality on your cellular phones. But later today we have much higher rates. Okay, for the reasons are very different today. So that's it about just converting. Converting symbol to samples. Okay, we discussed samples per second and bits per second. So both of them were actually sample rates. So once you sample it, what is the rate at which the signal is going to come? And we also very briefly discussed something called source coding, where you convert more number of bits into a smaller number of bits, provided you know some statistics of the source. Okay, we didn't go into the deeper mathematics of it. I just said that you can do that and you can reduce the number of bits. Okay, so that was one discussion. Now I'll probably discuss about the digital communications. Where does digital communications figure in here? I discussed right now, what I discussed is a very simple problem of source compression. So given a source, I'm going to represent it, sample it, convert it to number of bits and reduce the number of bits. So that process is called compression, or source coding. Okay, so first you have an analog source x of t. You are going to pass it through a PCM pulse code modulator, or simply I can simply say a sampler. Okay, that's going to, or properly to put it in a proper word, it's an ADC, analog to digital converter. I'm going to convert it to digital samples here, ones and zeros. Then I'm going to pass it through a block called as source coder, encoder. Okay, this is going to reduce the number of bits here. Okay, so this is what we said. Let's say this ADC is going to generate, this ADC is going to produce 12 to 13 bits here. The source coder is going to reduce it to 8 bits or 4 bits, depending on the quality of speech you are looking for. Okay, so it can reduce the number of bits here. So this is the whole operation that is done to the source before it is converted to what we call as waveforms. The next, that I'll discuss it in the next class.